dive into the basics of per phase analysis. And we were using the conversions to sort of lead up to the point where we could do per phase. So this time we're just going to continue from there. And hopefully get through a bulk of chapter 2 today, although I'm not exactly sure how much we have left, so that may or may not be realistic. Okay. Find where we left off in the notes here. Okay. So, we actually had a good stopping point. Section 2.4.4 is delta connection for machines and transformers. So we'll just write it like this: delta connection for machines and transformers. Essentially, right, any shunt connected device, meaning between the phase and the ground or the neutral, we're going to represent as either a Y or a delta connection. Okay, and then the next section, or little subsection in there, 2.4.4.1, they got a lot of subsections, is the delta-to-wye conversion. So we had said that we would talk about this, but we hadn't gotten to it yet, right? We haven't talked about the delta-to-wye conversion yet, right? Okay. So there's a couple different versions of this. The easiest is under balance conditions. So if under balance conditions, simply ZY is equal to whatever the Z delta connected value is divided by 3. So if we had something that looked like this, this would be our Z delta value. And if they're all the same, then our Y connected would look like this, where this would be labeled as Z delta divided by 3. Now, this only works this only works if everything's the same in all 3 phases. So when we say that it's Z delta, it's Z delta, Z delta, Z delta, and then the values on all 3 of the phases is Z delta divided by 3, Z delta divided by 3, Z delta divided by 3. Now, there are different expressions that we can use if it's unbalanced. So if the loads are not balanced, then we have a slightly more complicated looking version. So the delta and so the delta to y, and I'm only going to write this for one phase. You can see the rest of them on page 37. So I'm going to write ZA because you'll see the equation is a little bit long, and the other version, ZB, ZC, is a similar form, and just you have to essentially use the right corresponding values. So ZA is going to be equal to ZAB, ZCA. So right, these are the two adjacent values. ZAB is adjacent to node A, ZCA is adjacent to node A, and then that's going to be divided by the sum of all of them together. ZAB plus ZBC plus ZCA. And what I can do is I can call this right here, I'll give this a name, and I'm going to call it, well, I don't need to give it a name, we're not going to use it that much. Okay, now, delta or y to delta, we have one version which is ZAB, and that's equal to ZA, ZB, plus ZB, ZC, plus ZC, ZA, and that's going to be over ZC. And so here, you can sort of get the idea. The numerator is the sum of the products of all three of the individual line to neutral values together. ZAB, ZBC, ZCA, that's all the permutations. And the denominator is the only value that's not adjacent to our ZAB, right? ZA, ZB are both adjacent, ZC is not. All right, now, so what values do we use to define the machine, transformer, load, whatever we want to, however we want to describe it? How do we describe their behavior? We're going to use or maybe the better term is these values will depend on the ratings or the rated values of the of whatever, of X. Now the way that we define the rated values differs on how the component is defined. Sorry, I have a cold. So let's say there's two different ways to define a device. Okay, let's say we have resistive loads. Okay, keep it simple. We have three resistive loads, they're connected, three-phase system. We can define that load as one three-phase load, okay, considering the whole thing as one chunk. Or we can define them as three one-phase loads, okay, the individual phases. This may seem like, oh, well, that's just a semantics type thing, right? It doesn't really make a difference. Which, in some respects, that statement's not wrong, okay? It doesn't really have that much of an effect. But it does have an effect on the way that the ratings are defined. So if we define something, and if the problem, for your purposes more specifically, if the problem says that we have so if we have a three-phase component, then we're going to be using a line-to-line rated voltage and a three-phase rated power. Now, you have to assume these because not necessarily in every problem is it going to always tell you. It's going to say three-phase transformer, rated values, 208 volts, 1 megawatt power rating. It's not going to specifically state line to line, but it's not going to specifically state three-phase. So this is something that you have to, it has to be, I mean, not memorized, but it has to be something that you're aware of. The other way is you could have three one-phase or single-phase components. I'll underline the S, and in that case, the voltage could be line to neutral or line to line. But in both cases, it'll always be the single phase rated power. So if it's a machine and it tells you if it's a three-phase component, 3 megawatt rated, each individual phase consumes 1 megawatt. If you want to have that equivalent and it's 3 single-phase motors, then you would say the rating is 1 megawatt. Sum all three together would be 3 megawatts. Now, what's the difference here on the two voltage ratings? So what you'll see is that the ratings are going to be dependent on the way that it's connected. And this makes sense because the voltage that the rating that we're setting is actually the voltage across the device. Okay? Right? This is actually so both of these are the rated voltage across the single phase of the device. So it makes sense. If it's Y connected, that rated value is line to neutral. If it's delta connected, that rated value is line to line. So if you think about it in more general terms, for a three-phase component, they're always defining it the same way. They don't care the way it's connected. It's just like a black box. You hook up the terminals, and you're ready to go. When you have three single-phase components connected, you can't think of it as a black box because you're being given the individual ratings for each phase. Therefore, the power rating will always be single phase, and whether it's a line to neutral or a line to line rated value, that'll be dependent on how it's connected. Okay, now, the next section from the book, three-phase power, and then I wrote ... so I'm not sure if there's more to that section title, but I'll go back and add if we need to. Well, and I guess what it's essentially talking about is the conversion between single-phase and three-phase power, which is really easy. That's an easy one. Right. Three-phase power. Where this can be calculated as V I, and this is an equation we've seen before, cosine of the power factor angle plus J V I sine of the power factor angle. And this is equation 234 from the book. Not too much of a surprise there, right? Three-phase power would be equal to whatever the single-phase power is times 3. This is assuming balanced operation. If it were unbalanced, then it would be the sum of all three of those together. However, as far as ratings are concerned, if we assume that we're talking about ratings, the ratings, well, it would be very unusual for the ratings to be unbalanced, because that would mean that you have different components hooked up on the three phases. All right. So the next question we're going to ask ourselves, going back to the beginning of the class, we talked about how three-phase power would provide us constant instantaneous power. Okay, so we're going to answer that question now. So how does three-phase, what's the word I want to use? How does a three-phase system provide constant value of P three-phase of T? And what we're going to do now is we want to show mathematically that this works. Remember, we said in the beginning of the course that this is one of the advantages of the three-phase system, is that it's able to provide us this constant power. So in order to do this, We're going to handle this in, there's really two steps to proving this. The first is going to be to write the instantaneous power for all three phases. Okay, and so we have PA of T, we have PB of T, and we have PC of T. Going back to, and I forget what the equation number is, but this should look familiar to everybody. Going back to an earlier section, right? We know that they all share the same first component here. VI cosine of phi. VI cosine of phi. VI cosine of phi. Okay? Where, right, this is what we call the real power. V Okay, just to make sure you know that those are the magnitudes, right? Now, they all also have a second term. Which is going to have a cosine element. So it's going to be 2 omega t minus phi. That's for phase A. For phase B, it's going to be the same thing, except what? Shifted by, no, not shifted by 120 degrees, right? Because all the phases are the same. Again, we're working in a balanced, with the assumption of balanced operations, so we can shift by 120 degrees. And then down here we add. All right, so now the next part is we need to sum all three of these together.
And it's cosine for both proportions? Is it one of them sine?
Well, sine is for the definition of reactive power. No, in the instantaneous form, they're both cosine. If you go back, this is the old version of the notes. So, in the instantaneous form, they're both cosine. What you're thinking of is when we calculate the reactive power. So once we change this to the complex form, right, if we represent apparent power as a phasor, then the imaginary component is the reactive power, which is when we use the sign. It's a little bit, you have to draw a line between when we're representing it in instantaneous, as an instantaneous wave, the instantaneous power, and then the phasor form. All right, let's go back here.
Professor,
Yes.
what was the that second term called again?
So this represents, this is the time varying component. Which we which we just represent as reactive power. So it's the instantaneous representation of reactive power.
That's weird that it's called the reactive power, even though it's like
Well, there's no imaginary component if you're not in phasor representation. This is instantaneous,
Oh, okay, all right.
right? So there can't be any imaginary term.
That's like what you see on the scope.
Right, this is like what, yeah, exactly, what you would see on the scope. So right now we're just working with real numbers. Yeah, that's one thing not to get tripped up there is we have an instantaneous representation, we convert it to a phasor, and then we usually work with it in that form. So we only use this form of the equation small number of times at the beginning of the class, and we won't really, after this point, use it too much again. Right. Not much of this course is, or any power systems course, outside of transients, is really concerned with instantaneous values. Okay, so now, when we sum all three together, what do we end up with? Okay, so, this is long. I'm trying to think of what the best way is to write it. So, I'm trying to do a little bit less derivation in this class because I know sometimes I can write stuff on the board. It can take up a lot of time, and it's not necessarily the most important information for you to be looking at. So if you go back to the old section of the notes, what's labeled on the website is, I guess, 2016 to 2018. The whole derivation is done up there. If you're interested, you can see why and how it sums to zero. Essentially, what you have to do is use a trigonometric identity, and when you do that, everything cancels out to zero. Okay, but I think for the sake of time and just keeping these moving, and the fact that I'm not going to really be able to test you on, well, I'm not going to be testing you on trigonometric identities. Might be better if we just move past it. But there you can see it right there. And I'll put a section, I'll put a little note here. I'll say, you know, this proof, or not proof's not the right word, but the derivation is in the board notes. So, right, what you see is that summing all three of the phases together provides us a constant instantaneous power, because the three sum together to zero. All right, let's move on and try an example now. And it's just a per phase analysis example. Jumping a little bit forward, this is most likely what your next quiz is going to look like. like how I gave you a pretty good clue for quiz number 1. It was going to be something to do with complex AC systems, solving using basic circuit analysis. A lot of these sections of the text, it's pretty straightforward what you're going to be doing. So I would be prepared. As I said, I'm going to get the homework worked out, the assignments. But be prepared for, three-phase system given to you with Y and delta connected loads, Y and delta connected voltage sources, being able to convert everything to a Y connected form, solve the single phase analysis, and give me the values in three-phase. Our next quiz, I don't want to do it, we'll keep it on every 2 weeks. So our quiz got moved from Thursday to Monday. So what we'll do is not this upcoming Monday, but the following Monday. So that would be, and I'll give you reminders, whatever that would be, I guess. So Monday was the 11th, so that would be the 25th. So she's better at math than me. All right, 25th. All right, so now going back to this problem, what we have is a three-phase connected system. And to make it a little bit easier, I guess they haven't given us any transmission line component. So the resistance along the intermediate line is 0. All right, so we got our phase A, our phase B, our phase C. We got our VAN. We got our VBN. We got our VCN. We got our ZL. And does anybody have the textbook on them? No, I didn't bring mine with me. I really wanted to read it the way it's written in the textbook, because now I'm a little bit unsure what values the problem gives you and what values I kind of derived and just gave you in the beginning. All right, well, I'll have to sort of work backwards. Okay. You have the book?
Yeah.
Perfect. All right, so. All right. So I want to be very explicit about the values that they give us. They tell us that the voltage line to line is 208 volts. Okay. They tell us that the magnitude of the impedance is 10 ohms. And they tell us that the power factor is 0.8 lagging. Okay, so for this one, there's not really a need to go and interpret it from the ratings. They're nice. They give it to you very explicit. So this is here. Okay. Then we have the 208 volts. which spans from here to here, right? So that's that one. And lastly, they tell us that the load is at a power factor of 0.8 lagging. And it asks us to give them, calculate so what parallel capacitance is required in order to bring us to an 0.95 power factor? Sorry, what, I don't know if I said that right. What parallel capacitance is required to do the power factor correction? So this is a power factor correction example. Now, where's our cap going to go? Right, our cap is going to be placed here. So we could call this our ZC.
Just on one of the letters.
No, it's on all three. It's on all three. I'll draw the other ones like this. Just because there's not really enough room. But we'll, again, for per phase analysis, anytime we do something for one phase, we're assuming that we're doing it for all three of the phases.
Can you just draw them like one line?
Yeah, we're going to draw it as one line 5. This is going to be a similar issue that you see in a lot of these power system problems. They give you information in weird ways because they want you to show that you're proficient in being able to convert back and forth. Maybe there are easier ways of presenting this problem to you. Instead of giving you the magnitude of the impedance, they could have just given you the resistive and the real and the imaginary components. They could have given you the line to neutral voltage instead of the line to line. You see what I'm saying? Part of the problem is going and getting everything in the form that you need it to be in. All right. So let's use per phase analysis. First step here. So what is this going to look like as a single phase? We're going to have a line to neutral source, and we're going to have a single resistance or impedance, sorry. And we'll have our cap over here. Most of these values are not going to change, right? This is still going to be ZC, which is unknown. This is still going to have a magnitude of 10 ohms. Power factor is still going to be 0.8. None of that changes. The main thing that's going to change is that our voltage, we're going to need that as the phase voltage. And so that is going to be equal to, they tell us that it's 208. So V line to line divided by the square root of 3. And if we wanted to, we could shift it by the 30 degrees, but we don't really need to because right? We can just assume, just as easily as we assume that the line-to-line voltage is the reference for 0 degrees, we can just as easily assume that the line-to-neutral is the reference for 0 degrees. So you just have to be cognizant when you're doing that, because if you go back at a certain point and it asks you for the line-to-line voltage, if you've said already that the line-to-neutral voltage is the defined 0, then you would have to take into account the 30-degree shift. Okay, so what that leaves us with is 208 over the square root of 3, which is 120 with an angle of 0 degrees. Okay, next. We have to solve the circuit. Well, let me ask you. What's the main value that we need in order to perform power factor correction? Right, if you remember, we talked about this. Say it again? The apparent power, right? But specifically, we want to know what the reactive power is being consumed by the load, because we got to go back and we need that capacitor to be injecting the same amount. Yeah.
Just a question. How is there a power factor of 0.8 if the load is being resistant?
The load is not purely resistive. It's the magnitude.
Oh, right.
That's 10 ohms. So, yeah, it's not. But that's a good question. If it were purely resistive, then right. I mean, that would be the problem. Okay, so let's solve the circuit to find QL. Where QL, right, if we have this right here, this will be SL. We can say right here that this value we'll call SC. Or, really, more accurately, we know there's not going to be a real component, so we can call it QC. Okay, so let's find QL. How are we going to do that? Right, we know that. So let's start off by writing the equations that we know. We know that QL is going to be equal to the magnitude of SL times the sine of the power factor angle. Right, that's the primary equation you're going to start off with. QL is equal to that. Now, we don't have those values yet. But we do know that the power factor angle, right, this will be equal to the inverse cosine of the power factor. Right? And we also know that the SL value will be equal to, so the magnitude of the apparent power will be equal to the real power divided by the power factor. Okay, unfortunately, I don't know if that's going to help us too much because, right, we don't know the real power either. So what we're going to have to do is work off of the current. So we know so what I'll do is I'll cross this off. I'm going to say this is not very helpful. I can't spell helpful. A more helpful equation would be, right, we know S, L will be equal to VL times IL, and then furthermore, we know that this will be equal to V, and I forgot my conjugate, that'll be equal to VL times VL divided by ZL. Okay. And if we want to find just the magnitude, we can do that. We may not know what ZL is, but we do know what the magnitude of ZL is. So by taking that form of the equation right there and essentially putting magnitudes around everything, now we do have the numbers that are required to solve that guy right there. So that one will be helpful. So if I number the sort of helpful equations, we have 1 that's here that's helpful, we have 2 that's here that's helpful, and we have 3 here that's helpful. And so we can combine those together in order to give us what we need. We know the power factor, we know VL, and we know the magnitude of ZL. So even if you don't necessarily know how to address a problem from the beginning, writing down equations, trying to relate values together, hopefully using that process you can come up with everything that you need. Okay, so let's go ahead and solve this then. So I'm going to go and use equation, whatever we called sort of equation 3. We know that the magnitude of SL will be equal to the magnitude of VL squared divided by the magnitude of ZL. Now, I want to be careful with the what I'm calling things here. Up above I called this ZP, so I'm going to use that same, sorry, VP. So I want to use that same notation. That's the phase voltage. Alright. So that gives us 120 squared over the magnitude of 10, which then we have, I didn't get this value specifically, so 120 squared is what? 144, let's do it. 1440. 144.0 volt amps. Can someone confirm that for me? I can't do math up here. Okay, good. All right, then we have what we call equation 2, and the power factor angle will be the inverse cosine of 0.8, and so the value for that is 36.8 degrees, or 36.87. And now we can go ahead and plug this all back into equation number 1. Bringing that down. And so we know that QL will be equal to 1440 sine of 36.87 degrees. One thing that we can't ignore here is the sign of this angle. It could be positive or negative. Can anybody tell me why we know it's positive? Yeah? Because it's lagging, right? 99% of the time for these problems it's going to be lagging, but you don't want to get complacent on always assuming it's positive, and then you have that one exam problem where it's leading and then You know, that's what gets you. So positive because lagging. All right, so I did it a different way before, so I need to use the calculator. I got 864 var. Hopefully that's what we get here. Can someone actually do, this calculator's not very good. Just 1440 sine of 36.87 degrees.
Yes, correct.
Great. Okay. 864 var. So this is the value that we need to account for. And, but there's another step in here. Right, remember, we don't want unity power factor. We want 0.95. So that actually makes the problem just a teeny bit harder, because if it were unity power factor, we would already know, right, the QC value would have to be negative 864 var. But now we have to go and we can use the same equations to figure out what would be the QL value when we have a power factor of 0.95. Yeah.
Is there any situation where you would actually need 0.95 rather than more?
Sure, most definitely. If you want to know what your range is, right? So if, sure, it makes the calculations harder, but it might make the hardware easier, right? If you have a certain range of capacitances that are available to you, you'll say, okay, we just need to get within 0.95 or 0.9, and then you can look at what the, you know, what the values are that you need. All right, so we can just use the same equations again. So what's the QL value? So remember, we don't want unity power factor, we want 0.95, so we need to calculate the QL that corresponds to 0.95. So what is that value going to be? We can go ahead and just use the equations that we have already come up with. So QL for 0.95 will be equal to, so the 1440, that shouldn't change. Sine of the inverse cosine of 0.95. And so the new angle will be 18.19 degrees. And the new value of QL okay, actually, there's a question we have to ask ourselves here. So, doing it this way assumes, right, that the magnitude of the impedance, ZL, right, is staying the same. It's not going to stay the same, though, because when we add the QC in, that's going to become part of the whole thing, and so the magnitude of that ZL is going to change. So when we go from the first condition to the second condition, we need to ask ourselves, what is it about the load that's going to stay constant going from the 0.8 to the 0.95 case? No. The real power consumption. Okay? So, I'm going to need to do a little bit of erasing here, but I think it's actually a good so remember, we don't want unity power factor, we want 0.95, so we need to calculate the QL 0.95. Step number 4. Should be a 2. And the answer, right, we already said. Okay. So, the PL for the above, and I'm going to write the 0.8 up here to remind us that it's 0.8. That was 1440 cosine of 36.87 degrees. The value that I got last time was 1152 watts. So this is what is going to remain constant. So now the equations that we're going to use to calculate the QL are going to be a little bit different. We know this. But don't know, well, what it is that we really don't know is we don't know the magnitude of ZL in parallel with ZC, because that's the new equivalent load that we have there. So, make a long story short, I know this is a little bit of a convoluted explanation, but does everybody understand what we're saying there? In the initial problem definition, we were relying on the fact that, right, the current here was defined by this load impedance magnitude of 10 ohms. When we perform the power factor correction, the load actually, right, is going to be both of these together. So this value here, the 10 ohms, is no longer going to be applicable. The magnitude is going to get potentially larger. Well, it'll be larger. Actually, sorry, it'll be smaller. So what is that constant value that we hold between the 0.8 and the 0.95 conditions? The value that we hold constant is that real power. So we calculated a real power of 1152 watts, and that's what we're going to go off of for the next piece. Okay, so now, step 5. Does that make sense? We're going to solve for the reactive power at the power factor of 0.95 using our old value of PL as well as our new power factor. So this is what we carry over. So what equations do we know? Same thing again. Right, we know that QL will be equal to the magnitude of SL sine of the power factor angle. We know again that the power factor angle will be the inverse cosine of the power factor. So that's good because we know this. And then third, we know that the magnitude of SL of the apparent power will be equal to the real power divided by the power factor, which is good because we know this and we know this. So we could take this value and plug it in there. All right, so going ahead and solving that, what we're going to end up with is the magnitude of 1152 watts over 0.95 times the sine of the inverse cosine of 0.95. This is our power factor angle. This is the magnitude of our apparent power. And so the value that I got for that, for the new QL, and I calculated it as Q net. Oh, which is the same thing. Okay, so 378.65 var. And again, can somebody with a calculator just check that for me? Make sure that's right. Yep, okay, good. So, we know what our new value is of QL. All we have to do is, lastly, so the QPFC, power factor correction, is just going to be equal to the old value minus the new value. So we'll have QL at 0.8 minus the QL, well, you know what? Let me write this in a more formal way. The QL at 0.8 should be equal to, at 0.95, should be equal to what? So if we go back up to this picture here, we see that those two values are being summed together. What we call the QPFC or the QC, and then the QL. And if we rearrange this, we end up with QC is equal to QL 0.8 minus QL 0.95, which is 864 var.
Professor, did you write that?
Did I write it backwards?
I think so. Did you just subtract 0.08?
Yeah, I think I made a math mistake. Sorry. Yes. That was exactly what I was trying to prevent by writing it out piece by piece, and I ended up doing the opposite. Okay, so 0.95 minus 0.8. Thank you. All right, so now what we have is, where's that value? 378.65 minus 864 var. And what we end up with is a QC value of negative 485 var. And this makes sense because, right, we expect our capacitor to be a negative reactive power injection, or to be, to be a negative reactive power sink, which means a positive reactive power injection. And then lastly, if we want to, which in a lot of problems, they're not even going to ask you to do this. They're not going to care. But we can calculate the actual capacitance value, right? What's the if in farads, what would be the actual capacitor that you would have to place? And that hopefully should be very easy. You know that your reactance for the capacitor will be equal to the magnitude of the voltage across the capacitor squared divided by negative QC. Sorry. There's negatives on both sides, so they would cancel out. Positive QC. No. Keep trying to skip steps, and I'm tripping myself up on the math. I apologize. Okay. And so what is that? The voltage should not be changing because there's sources that are directly across the load, so that's 120 volts. So magnitude 120 squared over positive 485, which what I got was 29.67 ohms.
So that's the magnitude?
Well, reactance is a scalar value. If you want to talk about its impedance, it would be negative J 29.67. I see what you're saying, right? No. I'm copying my notes here. I'm skipping steps, which I should not be doing. Right, we know let's do this formally so the signs work out right. Okay, we know that SC, right, is equal to the voltage across the load times the current across the load through the cap conjugate, right? Sometimes I wonder if I just was doing it without my previous notes, I would actually be doing it faster. Okay. We have that equation there. So then we know that ZC for a capacitor is actually defined as I'm obviously having a brain thing right now. I'm not able to do this. The answer is 29.67 ohms. When I post the notes online, I'll go and clean up this, but I'm going in circles here. I'm wasting time. So I'm going to make a note to myself. I'll clean this up, and when you have the notes online, I'll make sure that it's more clear how to get that value. All right, so power factor correction. That's how you do it. And again, 90% of the time, it's going to be asking you for that bar value there anyway. 90% of the time, it's going to be more concerned with what the reactive power injection is, as opposed to what the actual reactance or what the capacitance value is. Okay, so the next topic is real and reactive power transfer. So this is section 2.5. And let me leave myself some room for when I clean this up. So let me move down a little bit. Okay, real and reactive power transfer. So one thing you'll note is that the previous example that we were just doing didn't have a transmission line. Okay, so we knew what the voltage was across the load itself. The next set of problems or type of problem that we're going to do will have a transmission line, and so this is not anything that's really new to you, right? You're used to working with DC problems that have a resistance or an impedance value between the source and the load. However, we're going to be incorporating it into our problems. Okay. The basic definition here, equation 242, not anything that is really groundbreaking. The current, right, along the line is going to be equal to the voltage at the sending minus the voltage at the receiving end divided by whatever the Z for the transmission line is. Okay? In most cases, or in a lot of cases, the transmission line will be assumed to be purely reactive, and so in those cases we'll have Vs minus Vr over J X L. Okay, so this is for the case with a purely reactive line. So how can we calculate the sending and the receiving, the power on both the sending and the receiving ends? And I'll draw this picture really quickly because it's not, right, we have voltage, we have impedance, we have a voltage. So this is a really simple system we can use to illustrate the line. Okay, we have this, we have voltage receiving, and we have voltage sending. And actually, I want to stay consistent with the letters, and so we'll call this T.
How could you ever have a purely reactive one?
You neglect the resistance. The value is small enough that you neglect it. I mean, it's a lot like how, like that power factor correction problem we just did. How can you ever have a capacitor without an internal resistance? It has an internal resistance. It's just that we're assuming that it's small enough that we can neglect it from the problem. Same thing here with the line. A lot of times what we see is that although it may be a little bit counterintuitive, you would think the resistance would be higher than the reactance, because the reactance is just attributed to the mutual inductance between the phases themselves. But actually the conductors are very good, so the resistance is low, and the mutual inductance has a pretty significant value or effect, and so that ends up being the dominating parameter that defines the way the line works. Okay. So the power, so we have two things. We have our SS and we have our SR. And so SR or SS is equal to the sending This is just some notation stuff. For the example, or for the material that we're going to cover in a second, drawing this relationship as a set of phasors will be helpful because it'll let us see visually how the powers change with the value of the X of the reactance. So let's draw that really quickly. So we have here the receiving voltage, which we are assuming is the reference with an angle of 0 degrees, right? Because in any system, we need to assume that one of the voltages or one of the values, it could be a current, it could be anything, current or voltage. We have to assume that one of those is providing the reference for the system, is the 0 degrees. So for this one, we're going to assume that VR has an angle of 0. That means that our VS the separation between VR and VS we're going to call delta. We also have our current, which we're going to assume has an angle of phi. This is the angle between, so it's the power factor angle for the receiving end, right? And I can put a little R there to indicate that. So that's the power factor angle for the receiving end. And so then what we can do is we can calculate VS using the end-to-end method. So this green arrow here is J times X I. Okay, so it's rotated by 90 degrees as well as extended by the length of X, or multiplied by the length of X. All right. Let's see how far I want to go. Yeah, I keep chugging along. Actually, why don't we discuss the project for a second, because I feel like we've done a lot of derivation today. This will be a good, not a good stopping point, but it'll be a good point to shift gears for a second. Okay, we'll pick up with this next time. We're going to be talking about specifically for this simple transmission line example, how does the value of the reactive element on the transmission line, which then plays into the power factor angle and the delta value between the phase shift along the transmission line, how does that play into the value of PR versus QR, and then going into this curve here, which is figure 218 from the book, and shows us